Outcome 1 is just the simple model of the atom. Describe a simple model of the atom. Okay, so a standard model of an atom might look something like that. Right? These are the electrons, right, round about the outside in orbit. The electrons are negatively charged. In the center we have the nucleus, which is made up of positively charged protons and neutrons which have zero charge. It's easy too. And it's explain attraction and repulsion. So opposite charges attract. So for instance, if you have a positive and negative charge, like charges repel. So positive and positive would repel, negative and negative would repel. Number 3, definition of an electric field then. An electric field is a space around a charged particle where another charged particle experiences a force. And because with charges you have both positives and negatives, and they would experience a force in opposite directions, then we have to pick one basically. So the convention is that the arrows that in the diagrams we're about to look at show the force on a positive charge. Continuation of 3 then is to draw some of the patterns, right, around a few particular things. So if you had a positive charge, then another positive charge would always what? Repel or attract?
So a positive and go away from repels.
Yeah. Repel.
So two of the same things.
Okay. So basically wherever I put another positive charge near this one, it's always going to push directly away. When we looked at this yesterday, we called it a radial field. Don't think you'll actually be asked that, but. And all these lines have arrows pointing away because another positive charge would experience a force or move in that direction.
Is this still 3?
Yeah. If it were a negative charge, what would it look like? If we had a negative charge in the middle? Yeah, they'd all go in towards it. In this next diagram, if we look at what would happen if you had a pair of similar charges. So I've picked the negative rather than the positive the last time, that we looked at last time. Okay, so a positive charge would be attracted towards the negative. And the same on this side. I'm going to shorten that one a wee bit. And if you're on that side, these would all be lines going in the way. But what would happen to a positive charge exactly in the middle of these two charges? If it was exactly in the middle, it would be attracted equally by both of them. So in actual fact, in the middle we have a wee zone where there's no force of attraction. Okay? But then what you have are these kind of curved lines. So basically you have to kind of push away from that zone in the middle where there is no attraction. And you get these curved lines like that. Now, it's not particularly useful, but the SQA have included it, so I need to include it as well. What's much more useful, though, is if we consider what would happen around a pair of oppositely charged. But imagine these were fixed and couldn't move. And now say to yourself, well, what would happen if I put a positive charge in the middle?
It would go very fast to the positive.
To the? Towards which charge, though?
The positive.
A positive would be?
Oh, no.
Yeah.
My bad.
Okay. So positive would move quicker towards a negative. So in a straight line exactly in between the two, it's quite straightforward. A positive charge would be pushed like that.
That's how it should be.
And then round the kind of far side, you've got the bits that are unaffected again. But what you have with the remainder ones is that they kind of curve round. So getting pushed away from the positive, it get pushed in towards that negative. So always getting away from the positive, always towards the negative. Now, actually the whole point of this stuff for this course is leading up to this last diagram. That if I have a plate, a couple of charged plates, so these green lines represent bits of a circuit basically. Okay, and if that was a positive plate, then what we really mean by that is that you've got positive charge all the way up and down it. And if that was a negative plate, you'd have negative charge all the way up and down it. And so the field lines for that would be like the middle, right, of this zone here. So this area here, that's what the field lines would look like. So you would always be going directly from positive to negative.
Do you always do the arrows as if it was positive?
Yes, that's what we meant by that idea. The convention is that they show the forces acting on a positive charge. So So this last diagram is important for what happens in circuits. Basically, because what is a circuit? Well, it's a complete loop connected to a battery, right, or other power supply. I.e., it's positive at one end and negative at the other end, which is exactly what we've just kind of shown in that sort of idea. So that idea of that uniform electric field, as it's called, the nice straight lines, is what happens when you attach wires to a battery. That's what you get in a circuit. Okay, learning outcome 4. In a conductor, electrons are free to move. That's what we mean by a conductor. So when we apply an electric field, to a battery, the electrons will move towards the positive end of the battery. And as we saw yesterday, they don't start in the battery, they're there in the conductors to start with. All the battery is doing is supplying the electric field, which gives them the energy to make them move. In contrast, in an insulator, electrons are tightly bound and generally won't move. Now, in extremes such as lightning, for instance, then you can start making the electrons in insulators move. But in normal situations, they don't move. So number 5 is the kind of descriptive definition of current. So now that we've got the idea of what's going on in a conductor, we can define electrical current So electrical current is a movement of charges, which is usually electrons, right, because it's not easy to make protons move, they're tightly bound to their nucleus. So that's a descriptive definition of current. The numerical definition, right, is given by the formula. So the numerical definition, Q stands for charge, which is measured in coulombs. I is current, measured in amperes. And it means charge per second. Right, the numerical definition of current is the charge passing a point in each second. So T is the time measured in seconds. When you actually had to memorize circuit Okay, example 1. Okay. Standard problem solving technique. Go through, find the information. Right, so there's our first number that we come across. It's meant to highlight. It almost looks like it scores it out, but or maybe underline rather. So the first thing I come across is the current. Calculate the charge that flows in this time. Now, milliamps is quite a common unit of current, so you'll find yourself probably come across that conversion quite often. Milli, remember, is 10 to the minus 3. The time is 3 minutes. That needs to be converted to seconds as well. So I've listed all the information I've been given in the question. Stage 2, what am I being asked? Shh. Okay, and then the obvious formula for this one, because it's a worked example for this one formula was just introduced. Q's are unknown, so we'll leave that as Q. I is 6 times 10 to the minus 3 times 180 seconds. Do the calculation, and we get 1.08 coulombs. Okay, now that was a straightforward example in terms of the formula. There was no rearranging required, but the numbers had prefixes and unit conversions. Example 2 will base on a reorganization. So calculate the current flowing . Okay, when 20 coulombs of charge pass a point in 5 seconds. Once again, go through, identify your numerical information in the question, and then start listing it. So this is why it's important you recognize the abbreviations for the units. The coulombs goes with Q for charge. The T is 5 seconds, and I is what you're trying to work out. Formula is Q equals IT. Substitute in what you know. Then how do I rearrange to get I? Now some of you might see that straight away, but I want to always do it right by doing all the basic steps, just in case some of you find that difficult. All the basic steps would involve swapping sides first of all to get I onto the left hand side, so I've not changed anything. And then you're saying, what do I have to do to both sides to get rid of the times 5 to get I on its own? Well, I have to divide by 5 because that cancels out the times 5, and whatever I do to one side of the formula I must do to the other. So on the right hand side I have to do 20 divided by 5, and I get my final answer then, 4 amps.